Alrighty. Hello and... Okay, sorry. Hang on. Of course, right as I start streaming, my kids get in a fight. You guys! My class is starting. Please whisper. Whew, okay. Hopefully they'll be able to hold it together for the next 80 minutes. Let's see. I'm not taking bets. All right. Okay, so welcome. It's Monday, new lecture, new week, and we are going to continue our discussion of molecular orbital theory. And we introduced this topic during Wednesday's lecture. And we concluded, hello, Kate, good afternoon. We concluded, at least, we concluded Wednesday's lecture with with drawing the molecular orbital diagram for hydrogen. And there's a feature of this diagram that I want to emphasize. I drew it on Wednesday in our last lecture, but I wanted to make sure to bring it home. Just to emphasize it. So again, I'm going to draw the molecular orbital diagram for hydrogen. Now, in the molecular orbital diagram, you have energy on a y-axis. All right. And you start with the orbitals for each. So this is the 1s orbital on one hydrogen and the 1s orbital on the second hydrogen. And these two drawn at these positions on the molecular orbital diagram represent the two orbitals, atomic orbitals on hydrogen, before they're close enough to bond with each other. And as you move to the center of the diagram, they get close enough to mix and form our two new orbitals. Now, the two orbitals that form, one is lower in energy because it is between the two nuclei. This is called the sigma bonding orbital. And then one is higher in energy because it's behind the two nuclei, and this is called the sigma star antibonding orbital. And to show that these two new molecular orbitals arise when you mix these two 1s orbitals, we draw these dashed lines from the atomic orbitals that mix to form the molecular orbitals on both sides. So those dashed lines signify that our sigma and sigma star orbitals form when we mix our two 1s orbitals together. And as we talked about at length on Wednesday, when you mix two orbitals, you make two orbitals. So we mix two 1s orbitals, and that's why we get a sigma and a sigma star. Now, hydrogen, has one electron in its 1s orbital. All right. And now when we mix our 1s orbitals together, these two electrons, we have to house these two electrons in the molecular orbitals that we made. And as we know, electrons always select the lowest energy orbital possible. So both of these electrons are going to occupy the sigma bonding orbital because it's lowest in energy. All right. We introduced the idea of bond order, right? Whether it's a double, single, or triple bond. And we said that the bond order of a molecule equals, or I should say the bond order between two atoms equals the number of electrons in bonding orbitals, which is 2, minus the electrons in antibonding orbitals divided by 2. So the molecule H2 has a bond order of 1, and that is consistent with the Lewis structure, right? We have a single bond between our two hydrogens. All of that we covered in Wednesday's lecture. The part that I want to emphasize here, so this is I didn't explicitly state this, and I wanted to today for you, you'll notice that when you go from two individual hydrogen atoms, all right, two kind of separate hydrogen atoms, to the molecule of hydrogen where they're both bonded to each other, that you'll notice that you start. So remember, this y-axis here tells you the energy level. And you can see that when you move from the two atomic orbitals to the molecular orbitals, that two electrons are stabilized. All right? Your electrons originally, both electrons are right here in energy, and they drop in energy when the two hydrogen atoms bond together. So these two electrons are more stable in the hydrogen molecule than they were in separate hydrogen atoms. And again, the reason for this is you have the hydrogen nucleus, which has a proton. You've got two of them, and that sigma bond holding the electrons are sandwiched. That sigma bond is sandwiched in between the two nuclei. So that is why it's more stable bonded than not bonded, all right? Because those electrons are now sandwiched in between two positive charges, and that's why it drops in energy. All right, so the reason, one could say the reason why the molecule hydrogen forms is because we've stabilized more electrons than we have destabilized. And with that in mind, let's move and draw the molecular orbital diagram for dihelium, all right, He2. All right, this molecule does not form, right? I said that in last lecture that we're going to start with a discussion of dihelium and why it doesn't form. And if I ask you the question why, you might say something along the lines of, well, helium's a noble gas, they're super stable, they don't like making bonds. All of that is true, but molecular orbital theory, as you will see, gives us the reason why, all right? So let's look at the molecular orbital diagram for helium. So energy is on the y-axis. Again, helium, just like hydrogen, if you look at its electron configuration, it's 1s2. So the only orbital we have in play is the 1s orbital. So for each helium atom, the only orbital we have to worry about here is the 1s. Oops, sorry. I shouldn't have put a square right there. So we've got the 1s orbital, and we know what happens when we mix two 1s orbitals, right? Same thing that happens when we mix two 1s orbitals with hydrogen. S orbitals mix to form a sigma bonding orbital and a sigma star anti-bonding orbital, all right? These two sigmas come from mixing our two 1s orbitals, so we draw dashed lines to show that these molecular orbitals form from mixing our 1s orbitals. So we've drawn, we've almost completed our molecular orbital diagram. Now we have to add the electrons. Now helium, unlike hydrogen, has two electrons in its 1s orbital. So each 1s orbital, atomic orbital that we start with also starts with two electrons. Now, to complete the MO diagram, we have to house all of our electrons in both atoms in our new molecular orbitals. And as always, electrons will fill the lowest energy orbital first. But there's a problem. Each orbital can hold a maximum of two electrons, right? So the sigma bonding orbital can only take two of the four electrons we need to house, right? And the only orbital left to house electrons is our sigma star antibonding orbital. If we calculate the bond order for dihelium, the molecule, bond order is equal to the number of electrons in bonding orbitals, which is 2, minus the number of electrons in anti-bonding orbitals, also 2, divided by 2. Now, 2 minus 2 is 0. 0 divided by 2 is 0. So dihelium has a bond order of 0. What does that mean? A bond order of 0 means no bond forms. All right, there is no bond between these two atoms. That's what a bond order of 0 means. Let's ask why. Well, if you look at this MO diagram, two electrons are stabilized right? At the same time, because we put 2 electrons in our antibonding orbital, 2 of our electrons are also destabilized. All right, meaning because we have 2 electrons stabilized and 2 electrons destabilized at the same time, that means that there is nothing holding these atoms together. In hydrogen, H2, hydrogen, those 2 atoms have to stick together because if they ever pulled apart, their electrons would destabilize. They get higher in energy. They want to stay at a low energy. But with helium, when they get close enough for their atomic orbitals to mix, 2 electrons are stabilized, but 2 electrons are destabilized, and so they literally just bounce off each other. There's nothing holding them together. They're not more or less stable together when they're apart, so they just collide and bounce off. Whereas hydrogens collide and then stay together because they're more stable together than they are apart. This is the reason why you do not see dihelium as a molecule, because it has a bond order of 2. All right, the real reason why the noble gases won't mix with anything else. And there's exceptions to every rule. We won't get into that right now. Okay. So that is the molecular orbital diagram for dihelium. All right, now, this kind of stuff is difficult to understand. It's definitely a very, it feels, especially at first, it feels like a bizarre way to look at bonding and orbitals. And if I'm being totally frank, this was one of the things that I struggled the most with when I took general chemistry as an undergraduate. And when I took Gen Chem the first time, I did great at everything else, but I didn't really get MO theory. It didn't stick right at first. But I decided to just kind of ignore it. And then to my terror, it came back when I was a chemistry major in an upper division organic chemistry class. And I was freaking out because I was like, this is the one thing that I don't understand. And so for those of you who, I'm introducing it now. Eventually I did. With enough practice, I was able to get it, and it made sense. I'm going to be very, very clear about our roadmap here with molecular orbital theory. We're going to look at 4 more atoms, all right? 4 more, I should say, molecules. And that will be the sum total of it. So we're not going to dive super deep, but I feel like it's important to show you this and expose it, because this is behind, if any of you end up studying inorganic chemistry, this will be your bread and butter, but also it also explains some of the most important reactions we see in organic chemistry. So for any of you who are OChem bound, this will have an impact on you as well. Yes, Kate, great question. So Kate asked, when I say destabilize, am I referring to the energy gain? Yes, and that is exactly what I'm referring to. Remember, electrons want to be as close to the nucleus as possible. They want to, because that's their lowest energy state. So the two electrons that gain energy, so to speak, the ones that are forced, into the sigma star antibonding orbital, these electrons are less stable they're less stable because they are higher in energy. All right, that's exactly what I'm talking about. Okay. Right. So where we're going with MO theory, we're going to look at 4 more cases. Totally, Kate, you are so welcome. Thank you for asking. So we're going to look at the MO theory, or sorry, the MO diagrams for difluorine. We're going to look at dineon, dinitrogen, and dioxygen. All right, these are the ones that we're going to look at, and these are the molecules that you will be tested on. This stuff, MO theory, will not be on the 4th exam. It'll be on the final, just for the record. Now, next up, we're going to look at F2. But before we do, we need to talk about some mixing. So if you look at the electron configuration for fluorine, and here I'm going to draw out the full electron configuration. It's 1s2, 2s2, 2p5. All right. Before we can draw the molecular orbital diagram for fluorine, for difluorine, and calculate its bond order, we need to take a little bit of time and we need to talk about how we need to talk about mixing p-orbitals. All right, we already know that our 1s is going to mix, our two 1s orbitals will mix to make sigma and sigma star. Our 2s orbitals will mix to make a sigma and a sigma star, but our p orbitals mix in a slightly different fashion, and so we need to kind of delve into that before we draw the molecular orbital diagram for difluorine. So let's talk about mixing p orbitals. All right, first off, we have 3 different p orbitals that we need to talk about mixing. All right, we have px, PZ and PY. I'm going to begin with mixing PY, all right? When you look at PY as an orbital, I'm actually going to drop it down here. PY is oriented along the in-plane horizontal axis. That's kind of an ugly one. I can do better. All right. I still think I can do better, but that's about as good as it's going to get. PY can engage in direct orbital overlap just like your s orbitals can. All right. So when you mix PY, there are two ways you can mix them. It can mix in phase and out of phase. And when, because again, we can form, so there are two ways we can phase PY. Either so if these two mix in phase, all right, so if they're going to mix where we put the clear orbitals together and the shaded back behind, this is constructive. This is constructive orbital overlap, and it is going to result in the formation of a bonding orbital. All right. It is going to result in the formation of a sigma bonding orbital. Oops. So when two p orbitals engage in constructive orbital overlap, when two py orbitals engage in constructive orbital overlap, they form a sigma bond, all right? When they engage in destructive orbital overlap, whoa, hang on. Here, I'm just going to use, there we go. All right, when they engage in destructive orbital overlap, in other words, when you mix them and they're out of phase, this is where you get destructive orbital overlap. And that destructive orbital overlap creates a sigma star antibonding orbital. What happens is those two orbitals in the middle, the two lobes of the orbitals that are out of phase in the middle, cancel each other out, and you form a sigma star antibonding orbital. All right, here and here are the two lobes of the antibonding sigma star. So when you mix two py orbitals together, you make a sigma and a sigma star, all right? So py mixes to make sigma and sigma star. Now let's look at what happens when you mix px and pz. We're going to start with pz. So when you look at pz, right, it's in plane, up and down. Now, the two ways you can mix pz are, you can either have them in phase, like so. Or you can mix them when they are out of phase, like so. And as we saw before, now with PZ, this is indirect orbital overlap, so we're not making sigma bonds, right? Indirect orbital overlap makes pi bonds. This is constructive. All right, here we have constructive orbital overlap. And here, when they're out of phase, this is destructive. Destructive orbital overlap. I'm going to give myself a little more room to work here. When you mix your two pz orbitals in a constructive fashion, what you get is a pi bond. Whoa, that's an ugly pi bond. Let me try that again. All right. So that is a pi bonding orbital that comes from mixing our two pz orbitals together. When you mix them destructively, you get an antibonding orbital known as pi star. And it looks like this. These are the four lobes of the pi star antibonding orbital. All right, again, you get this pi star antibonding orbital from mixing your two pz orbitals together in a destructive fashion, right, where they're out of phase. And both of these lobes, or all, I should say all four of these lobes, belong to the pi star antibonding orbital. So py makes a sigma and sigma star, pz makes a pi and a pi star. Let's take a look at what molecular orbitals form when you mix px. All right. Now with px is it's a little weird. You'll recall it is coming out of the board at you and then back behind the board away from you. So you kind of get this head-on look. I should space this out. Okay. Now, just like PZ with PX, PX engages in indirect orbital overlap. So when you mix these two together and they're in phase, hang on. So when these two are in phase, need to move these over. When you have the shaded and unshaded sides matching, this is constructive orbital overlap. And it results in the formation of a pi star, or sorry, a pi right, where one is in front and behind. This is a pi bonding orbital formed from px, mixing these two px orbitals together. When you mix these in a destructive fashion, so when your phasing's off, you get destructive orbital overlap. All right, destructive orbital overlap, and this makes a pi star antibonding orbital. It's a little hard to draw. When it's kind of in front and behind, but this is the pi star that forms from the destructive orbital overlap of these two px orbitals. And again, all four lobes here belong to the pi star antibonding orbital. All right, so here's the big take home. All right, direct orbital overlap which is py, results, so direct orbital overlap from py results in the formation of a sigma bonding orbital and a sigma star antibonding orbital, and the indirect orbital overlap so the indirect orbital overlap from px and pz results in indirect orbital overlaps from px and pz results in two pi bonding orbitals and two pi star antibonding orbitals. All right, and the reason why you make two of them is because you have two p orbitals that engage in indirect orbital overlap. Px makes its own pi and pi star, pz makes its own pi and pi star. All right, now we need to talk about orbital energies. All right, how do these rank? All right, how do you show this in a molecular orbital diagram? All right, now in a molecular orbital diagram, all of the p orbitals, px, py, and pz, are all equal in energy. All right, so often the way you show this is when you have your p subshell. So for example, your 2p subshell, you show this by stacking all three of them together. All right, so these are our 2p orbitals. All right, we stack them here to show that all of these are equal in energy. All right, but we have to show them we have to show three distinct orbitals, and when you crunch them together like that, it means that they're all at the same energy. You can write them out like side by side in a line. Space gets to be a little bit of an issue, so you won't see me doing that, but if you want to, that's also totally okay. But I just want you to know that even though there's a spacing between them, when they're clumped together like that, that means they're equal in energy. Now, the question is, what are the orbital energies? All right, we've talked about we make one sigma star, two pi star, but where are they relative to each other? And The sigma bond, the sigma bond is always going to be lowest in energy. All right, so that sigma bond is lowest in energy because it's sandwiched between the two nuclei, followed by the two pi bonds. So the pi bonding orbitals are equal in energy, the one formed by px and pz. So we show them two stacked, followed by the pi star antibonding orbitals and the sigma star. All right. Now, just like every orbital diagram that we've drawn before, whenever we draw our molecular orbitals, we have to show the orbitals that are mixing to form them. And we signify this by drawing dashed lines in between the atomic orbitals we're mixing and the molecular orbitals that we are forming. All right, so you do dashed lines from the p orbitals that are forming the pi star, sigma, and sigma star, and all of those molecular orbitals. I realized I forgot to put my star up by my antibonding orbital. All right. Now, so that is how you show your p orbitals mixing. You have 6 p orbitals total, right? 3 on each side. So you're going to mix to make 6 orbitals: 1 sigma, 2 pi, 2 pi star, and then 1 sigma star. Those are your 6 orbitals. They'll always be ordered like this. I have to make a note. Kate, I'm going to wait to answer your question until after I say this one. Let me say one more thing, and then I'll answer your question. So I said that these are the orbital energies that your orbitals will always fall in. I do have to say there's one exception. And the exception that you need to know is for nitrogen, for N2, the energy levels of the sigma and the pi switch places. So for nitrogen, it's actually you have your pi bonding orbitals that are lower in energy than your sigma. Your pi star and your sigma star are not changed. Oops. So for nitrogen, pi star and sigma star remain in the same place. All right, so that's what happens when you mix your p orbitals for N2. All right, you end up with this situation. All right, that's our dinitrogen exception. Technically, and if for those of you who read the book, you'll see this, this is the order of orbital energies for also C2 dicarbon and diboron. But I'm not going to mention these or test you on them because dicarbon and diboron don't exist in nature. All right, so even though technically there's more atoms that have that reversed orbital energy, nitrogen N2 is the only one that exists in nature that has this inverted energy of the sigma and the pi bonding orbitals. So that's the only one I'm going to test you on. Now, Kate, the answer to your question, when you make a pi bond, do you also make a sigma bond? The answer to that question is that your electrons will always fill the lowest energy orbitals first. So, with that in mind, for nitrogen, you're actually going to fill, you make your pi bonds first. Because your lowest energy orbitals are pi orbitals. For everything else, you make your sigma bonds first. So for any molecule that is not nitrogen, if you're making pi bonds, you already have a sigma there. For nitrogen, you make the pi bond before you make sigmas. But the thing is, even in nitrogen, it still has a sigma bond. So even there, you'll have a sigma together with your pi. But technically, the pi will form first. All right. Now that we know how to handle the mixing of our p orbitals, we're ready to draw the molecular orbital diagram, or remaining molecular orbital diagrams for F2, for difluorine, di-neon, di-nitrogen, dioxygen. All right. So let's start with difluorine. So we have our y-axis with energy, and often I find that it is it's helpful for writing these MO diagrams to write out the electron configurations. All right, so let's write out the electron configuration for fluorine, because it's going to help us with our MO diagram. Fluorine is 1s2, 2s2, 2p5, all right? The reason why I like writing out the MO diagram is it tells me which orbitals I'm dealing with and how many electrons are in each orbital. So I'm going to start with writing in my 2p orbitals, my 2s orbital, and my 1s orbital. And the fluorine on the other side has the exact same setup. We've got 3 2p orbitals, 1 2s orbital, and 1 1s orbital. All right, now we know how our orbitals are going to mix. All right. Well, before we start mixing orbitals, I'm actually going to put our electrons in place where they go. So we have 2 electrons in our 1s orbital, so they'll go there and there. We have 2 electrons in our 2s orbital. Finally, we have 5 electrons. Whoops, I wanted that in blue. 5 electrons in our 2p orbitals, and so here they'll go 1, 2. Whoops. I'm going to try to draw this as clearly as I can. 1 and 2, 1 and 2, and then just one single one. So 1 and 2, 1 and 2, and then one single electron. All right, now we need to mix these orbitals. So our 1s orbital, our 1s orbitals, actually I'm going to just Move this down just a little bit. These are going to mix to form a sigma and a sigma star. All right, so that's these two 1s orbitals mixing. My 2s orbitals, I'm just going to nudge these up just a little bit. My 2s orbitals are going to mix to form both a sigma and a sigma star. And then my p orbitals, as we know, will mix to make sigma, pi, pi star, and sigma star. All right, and these, we show them mixing here. All right, now we've written our molecular orbital diagram out. Now we need to take all the electrons in our atomic orbitals and place them into the molecular orbitals that we have created by mixing these atomic orbitals together. Now, starting with our first energy level, right, you'll notice that we have a total of 4 electrons to house, right? There's 2 electrons in our in each 1s orbital. We've got 2 of them, right? So we've got 4 to place. So we're going to put our first 2 electrons in the lowest energy orbital available, the sigma. Next, we're going to place our next 2 electrons in the next lowest energy orbital. And you'll notice that the sigma star made from the 1s, the mixing of the 1s orbitals, is the next available orbital with the lowest energy. So 2 electrons go in there. Now we have to house our green electrons, right, in our, that originally were in our 2s atomic orbitals. The first 2 will go into our sigma, which is the sigma from mixing our 2s orbitals. The latter 2 will go into our sigma star. All right, so we've housed our electrons from the first energy level. We've housed our electrons from the 2s subshell. Now we need to house our p orbitals, and you'll notice that we have 5 on each side, so we have to place 10 electrons total. And you'll notice I've signified those by using the color blue. The first 2 drop down into sigma, so there's 1, 2. The next 4 will go into our pi bonding orbitals, right? And we have 2 pi bonding orbitals, so we can house 4. So there's 1, 2, 3, 4 on the lower 2. We've housed 6. We have to house a total of 10. So the next 2 go into, the next 4 actually go into pi star. So this is, now we've placed 10 electrons that came from our 2p subshell. We've housed all of the electrons from the molecular orbital, in our molecular orbital diagram. We're now ready to calculate our bond order. Now you'll recall that bond order is equal to bonding electrons minus the anti-bonding electrons divided by 2. All right, now our bonding electrons are all electrons in bonding orbitals, all right? So we've got 2, 4, 6, 8, 10. 10 total electrons in bonding orbitals, right? Minus all of the electrons in antibonding orbitals. So we've got in antibonding orbitals now 2, 4, 6, 8. So 10 minus 8 divided by 2 gives us a bond order of 1. Molecular orbital theory predicts a bond order of 1 for the molecule of F2. And you'll notice that is also consistent with our Lewis dot structure. If you look at the Lewis dot structure for F2, it has a single bond, which is what a bond order of 1 actually means. All right, so there's the molecular orbital diagram and bond order of the molecule difluorine, F2. Let's look at the molecular orbital diagram for dineon. Now you might be going, wait a minute, neon's a noble gas. I thought noble gases didn't like to bond. Well, let's write the molecular orbital diagram, draw the molecular orbital diagram, and calculate our bond order. Let's see what happens. If you look at the electron configuration for neon, it's 1s2, 2s2, 2p6. All right, so we put energy there. Now neon has, we've got our 1s, our 2s, and our 2p orbitals for both of our neon atoms. So they're the same on either side. Now, when it comes to placing our electrons, we have 2 electrons in our 1s orbital. We have 2 electrons in our 2s orbitals. And here we have 6 electrons in our 2p subshell. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, now we got to mix our orbitals together. So our 1s orbitals mix to form a sigma star and a sigma. Our 2s orbitals mix to form, same deal, sigma and sigma star. Whoa. There we go. And then our p orbitals mix to form sigma 2 pi, 2 pi star, and sigma star. And all the glorious dashes that accompany them. All right, now let's house our electrons. We have a total of 4 electrons in our atomic 1s orbitals. The first 2 go into that sigma, the next two go into that sigma star. We have 4 electrons in our 2s orbitals that populate both sigma and sigma star. Finally, for our 2p subshell, we have 6 electrons in 1 neon, so that's 12 electrons total. Our first 2 go into sigma. Our next 4 occupy our pi bonding orbitals. The following 4 occupy pi star. So let's see, that's 10. Our last 2, therefore, have to occupy sigma star. Now let's calculate, this is the molecular orbital diagram. Let's calculate the bond order. Remembering that bond order is equal to bonding electrons minus, whoa, hang on. Bonding electrons minus antibonding electrons. Divided by 2. So, for bonding electrons, we have 2, 4, 6, 8, 10. We have 10 bonding electrons. Minus, now for our antibonding electrons, we have 2 in the sigma star plus 2, so 4 in that sigma star. 8, 10 as well. So our bond order here is 10 minus 10 divided by 2, which means our bond order is 0 for dineon. Again, that means that no bond forms. All right, no bond forms. And that is also consistent with what we know from the Lewis structure of neon. Neon has 8 electrons. It's already completed the octet rule. It has no need to make a bond with anything else. It already has all the electrons it wants. That is why our bond order here is 0. All right? So let's do, we've got 2 more to do, dinitrogen and dioxygen. So looking at nitrogen's electron configuration, it's 1s2, 2s2, 2p3. So here's our y-axis, and starting with our 1s orbital, next we write our 2s orbital, and finally we write our 2p. And it's mirrored on the other side. 2p, 2s, 1s. All right, now nitrogen has 2 electrons in its 1s orbital, 2 electrons in its 2s orbital, and 3 electrons in its 2p subshell. And you'll recall that electrons would rather not share an orbital if they don't have to, and there are 3 electrons, 3p orbitals, so they're all singly filled. All right. Next, we need to start mixing our orbitals together. Our 1s will form a sigma star and a sigma. Oops. Forgot to draw my line for sigma. There we go. Oops, hang on. Sorry, it's not. There we go. Just needed to adjust that. So our 2s orbitals also making sigma. Oh, hang on. A sigma and a sigma star. All right, and then finally we have our 2p orbitals, and you'll recall that this is where it flips around. The pi bond for nitrogen is actually lower in energy than sigma, so we draw pi on the bottom and sigma up top, but pi star and sigma star remain in place. So pi and sigma are the only two you have to worry about switching when it comes to nitrogen. All right, now let's place our electrons. We have 4 electrons in our 1s orbitals. These will be housed by the sigma and sigma star. We mixed from them. Same story with our 2s. We have 4 electrons to house, and we made a sigma and sigma star that will hold those electrons. Now, with nitrogen, we have 3 electrons in each p subshell, so that's got 2 of them, so that's a total of 6. Our first 4 land in our pi bonding orbitals. The remaining 2 land in our sigma, and now we're out. All right, we are out of orbitals. It is time to calculate the bonding, the bond order, excuse me. So first we look at all of our bonding electrons. We have 2, 4, 8, 10. So we have 10 electrons in bonding orbitals. And now we subtract our anti-bonding electrons. We have 2 down in the sigma star, plus another 2, so that's 4. And those are all the electrons in anti-bonding orbitals. We take this difference and divide by 2. So we get a bond order of 10 minus 4 is 6 divided by 2. And so we get a bond order for nitrogen of 3. And when you compare this to the Lewis dot structure, nitrogen does indeed have a triple bond, so you can see that these 2 are consistent with each other. They're different ways of looking at the same phenomenon. All right, now, at this moment in time, you may be asking, okay, Josh, what's the point of any of this? You might be saying, like, okay, yeah, like seeing that 0 bond order for dihelium or dineon was cool. Like, oh, that's the reason, and I can see it visually. I understand it better now, maybe. But you might be thinking, all of this is crazy confusing. Why? Why? Especially because it's only been telling us things that we already knew. We already knew that fluorine has a bond order of 1, or that nitrogen has a bond order of 3. We already knew that helium and neon didn't bond. So what's the point of any of this? And I'm so glad you asked, or I guess I asked, if you were wondering. I'm glad you're thinking those thoughts, because MO theory is not just a new, more confusing way to tell you what you already knew from Lewis structures. It was developed because there are phenomena in nature that Lewis theory cannot explain. Lewis theory cannot explain, but molecular orbital theory does. Where it really shines is in the transition metals, in the D block. The reason why we never drew a Lewis structure for a metal is because Lewis theory does not explain the bonding or reactivity that we observe for transition metals. Molecular orbital theory does that in spades. We're not going to go there, though, because this is Gen Chem, and inorganic chemistry is an upper division course. So if you're interested and want to see more of that, head in that direction. We do have one shining example, though, that is Gen Chem appropriate, that shows you how molecular orbital theory describes something that Lewis theory cannot. All right? And that is where our example of O2 comes in. Let's talk for a minute about dioxygen. All right. The first thing, so I want to tell you something that's true about oxygen. O2 is what's called a diradical. All right, O2 is a diradical. You probably have heard the word radical floating around, probably mentioned in the context of health foods, probably mentioned along with something called antioxidants. All right, we all hear antioxidants and we're like, oh, that's good for us, right? Antioxidants are good. Free radicals are bad, right? And that's actually correct. All right, free radicals are can do tons of damage to your body, and antioxidants react with them, kind of neutralize them, take them out of the equation. But what is a radical, or what's known as a free radical? A free radical is a species. It doesn't have to be a molecule. Sometimes it's just an atom. I don't think there's an I there. A free radical is a species with a single unpaired electron. All right, usually something that's violating the octet rule. These things are very reactive. They can do all sorts of damage to your body, to your DNA, all that kind of stuff. They're very reactive. I should probably spell that, because people will be wondering, what's V reactive? Very reactive. They cause bodily harm, all that stuff. All that stuff that we're afraid of, all right? Now, oxygen, you'll notice, is a diradical. That means that oxygen, the molecule, has 2 unpaired electrons. All right, 2 unpaired electrons. Double, toil and trouble. But if you look at the Lewis structure for oxygen, it just looks like this. Where are the radicals? Where are the unpaired electrons? I see everything in a lone pair or a bond. There's no radicals in this Lewis structure. This is where molecular orbital theory steps in and shines. Let's draw the MO diagram for O2. All right, let's actually draw this molecular orbital diagram, starting with the electron configuration: 1s2, 2s2, 2p4 is what oxygen has. All right? Yes, because it's one more than nitrogen. So we've got energy on our y-axis, starting down low with our 1s, followed by our 2s, followed by our 2p. Right, we've got the same thing on the other side. 2p, 2s, 1s. Placing our electrons, we have 2 electrons in our 1s orbitals, 2 electrons in our 2s orbitals, and 4 electrons in our 2p. So that means we're going to have 2 unpaired and 1 paired in atomic oxygen. All right, now let's do what we do best and mix these atomic orbitals together to make our molecular, to complete our molecular orbital diagram. So there's our sigma star and our sigma coming from our 1s orbitals, followed by our sigma and our sigma star coming from mixing our 2s orbitals together. Finally, we need to write out our sigma pi star, which, for emphasis sake here, I'm going to draw the 2 pi star orbitals side by side. You'll see why in a minute. And sigma star. All of these come from mixing our 2p orbitals together. All right, let's take a look. So first we mix our electrons from our 1s, or we've already mixed our orbitals, so we're going to house our 4 1s electrons in our sigma and our sigma star. Next, we house our 4 2s electrons in our sigma and our sigma star. Now, for our 2p electrons, we have 4, but we've got 2 oxygens, so we have 8, a total of 8 electrons to house. The first 2 go into sigma. The next 4 go into pi. Now we have 2 electrons left, and you'll notice that we have 2 pi star orbitals that are equal in energy. So we have to put 1 in one and 1 in the other, because electrons would rather have their own orbital because their like charges repel each other. Let's calculate our bond order here. Bond order is bonding electrons minus antibonding. So we've got for bonding 2, 4, 6, 10. 10 bonding electrons. Minus our antibonding electrons. We have 2, 4, 6. So 10 minus 6 is over 2 is 4 over 2, giving us a bond order of 2. And we knew that. All right, we know we had a bond order of 2. Our Lewis structure tells us that we have a bond order of 2. But there's something important that our Lewis structure does not tell us. All right, Lewis structure does tell us a bond order of 2. But here where oxygen is a diradical. Oxygen is a diradical because it has 2 unpaired electrons in the pi star antibonding orbitals. And nowhere in the Lewis structure, Lewis theory doesn't have a concept, doesn't have a category for bonding orbitals versus antibonding orbitals, but the 2 electrons that are housed in the antibonding orbital, the pi star antibonding orbitals, are unpaired, making oxygen a diradical. Now, it's possible to draw a Lewis structure where oxygen's a diradical. You can do it if you take this bond and give 1 electron to that oxygen and 1 electron to that oxygen. All right? You can technically draw a Lewis structure where oxygen has 2 unpaired electrons. If you do, it'll look like this. There's a problem with this structure, though. It breaks the octet rule for both oxygens. If you count up the number of electrons each oxygen has access to in this structure, yes, it shows each oxygen with an unpaired electron, but each oxygen only has access to 7 electrons. Only in the molecular orbital diagram do you get the full picture. Do you have oxygen with a completed octet and oxygen with 2 unpaired electrons? Also, you'll notice that 1 in the 2 Lewis structures, not only does the second one break the octet rule, but 1 you have a double bond order of 2. The other one you have a bond order of 1 and 2 unpaired electrons. Only in the molecular orbital diagram do you get an actual bond order of 2 depicted and the diradical together, both present, both accounted for. So really, this is the only way to fully depict all of the truth, all of what we know to be true about the molecule O2. It only comes at us from molecular orbital theory. And that sort of completeness, that sort of thoroughness is what molecular orbital theory, what MO theory shines in for the reactivity and behavior of the transition metals. This kind of gives you that first glimpse of, whoa, this is something new. This is something more than what Lewis theory was able to show us. If this whets your appetite, there's more for it, but it lies outside the confines of general chemistry. All right, this concludes our discussion of MO theory. Again, it's not on exam 4. It will be present on the final. We will pick up on Wednesday talking about intermolecular forces and the effect that intermolecular forces have on colligative properties. Anyways, I hope you all had a great Thanksgiving. I will catch some of you later in office hours. And if not, I'll see you in lecture on Wednesday.